Welcome back. In previous session, we have seen that the derivation of inverter ratio in the situation like the inverter driven by another inverter without any pass transistor. In that situation, to get the symmetrical operation or to avoid the voltage degradations, the ratio must be 4. Similarly, let us take another situation. The situation is through a pass transistor, an inverter is driven by another inverter. So in this case, how much inverter ratio we have to maintain to get the symmetry, that we have to see now. For that purpose, here the slide representing an inverter driven by another inverter through number of pass transistors. Okay. So here what happens is, because of the pass transistor presence, though the output of first inverter is VDD, the input at the second inverter is not equal to VDD. That is always less than VDD, that equal to VDD minus VTP. So whatever the output value we are getting with VDD input, the same output value we need to get with the input VDD minus VTP. Then only you can get the symmetrical operation. So for that purpose, this is the derivation we are going to do now. How much the inverter ratio we can get, that we will see. With the input VDD, let us consider the equivalent circuit of first inverter, and with the input of VDD minus VTP, the equivalent of second inverter is like this. With input VDD means what happens? The pull down transistor in on state. That too, it acts as in the active region or non-saturation region. Why? Because since it is in on state, the VDS voltage across pull down transistor is very less. Okay, so the transistor operates in non-saturation, hence it is represented by a resistor. Whereas the pull-up transistor is in the saturation, since large amount of VDS voltage is there across this transistor, hence it is in saturation and act as a current source. In the saturation, the MOS transistor act as a current source. So therefore, this is the equivalent circuit for the first inverter transistors. Similarly, in the second inverter case also, the pull down transistor is represented by a resistor R2, whereas pull up transistor is represented as current source with the current I2. With this, let us see the currents of each and every transistor and also resistance value like that. For the pull down transistor, it is in non-saturation region. Therefore, the current with reference to pull down transistor is IDS equal to K WPD1 divided by LPD1, that is pull down transistor width divided by pull down transistor length of the first stage, right? Of actually formula is VGS minus VT. Here VGS is how much for the pull down transistor? VDD minus VTN, that is the pull down transistor is enhancement NMOS, therefore its threshold voltage is VTN minus VDS1 divided by 2 into VDS1. This is the current for the pull down transistor. Okay. Now the resistance R1 is given by resistance R1. How can you get? Voltage divided by current is the resistance. Therefore R1 equal to VDS1 by divided by IDS1 equal to, from the previous equation, okay, the ratio VDS1 by IDS1 equal to, you can write 1 by K into LPD1 divided by WPD1 into 1 by the voltage term. Okay, since already with reference to pull down transistor, the VDS voltage is very small, since it is in active region, right? That to non-saturation region. That means that half of the VDS means it is very small, that's why it is neglected. And with the rest of the parameters, the R1 value is expressed like this. Now R1 equal to ZPD1 divided by K into 1 divided by voltage term. The voltage is VDD minus VT. Where what is ZPD1? Z is the aspect ratio, right? That is L by W. L by W is represented as ZPD. Okay. This is the resistance R1. Similarly, for the second stage, okay, before going to the second stage, let us see how much I1 current flows with reference to pull-up transistor. Since the pull-up transistor is a depletion transistor and its VGS is 0, the two the transistor operate in the saturation region. Therefore, its current is I1 equal to, that is saturation current equation, kW by L into VGS minus VT whole square divided by 2, that is the actual basic equation. Now VGS is 0, that's why that VGS term is absent here, minus VT means VT dP whole square divided by 2. Hence the product R1 and R2 is, substituting the I1 value, this is the I1 value, and R1 previous equation we derived previously, that is the Vout. Okay, so Vouts of both the inverters should be equal, that is our condition, right? In both the situations, situation means when the input is VDD, whatever the amount of output voltage we are getting, with the VDD minus VTP also the same amount of voltage we can expect. That we have to see. Now with VDD input, the product I1 R1 equal to, that is Vout is treated, that equal to, substituting the I1 R1 derived equations previously, the equation becomes like this. Okay, this is I1 R1. Now see, with the input VDD minus VTP, what will happen? Okay, if the suppose with the VDD minus VTP applied as an input, the pull down transistor again in the active region, so that its resistance, its current value with the current finally deriving the resistance value is like this, R2 equal to ZPD2 divided by K, similar to R1 derivation, it is also 1 divided by VDD minus VTP minus VTN, and I2 is derived like K into 1 by ZPU2 into minus VTD whole square divided by 2. The way how the R1 I1 is represented, similarly here R2 and I2 represented, but the difference is where the input is VDD voltage, but here the input is VDD minus VTP. Okay, so with this the product I2 R2 equal to, substituting these two I2 R2 equations, the Vout2 is like this, Vout2 is like this. Okay, now we equate the Vout1 equal to Vout2, because you need to get the same output voltage, right? The output voltage with the input VDD should be equal to the voltage when the input is VDD minus VTP. Okay, that's why we are taking the condition Vout1 equal to Vout2, that is I1 R1 equal to I1 I2 R2. So by substituting the above products and simplifying the equation is like this. Now substitute the typical values for each and every voltage parameter. That is, VTN is 0.2 times of VDD, VTP is, that is threshold voltage of pass transistor, it is 0.3 times of VDD. The resultant one is the ZPU2 divided by ZPD2 is equal to 2 times of ZPU1 divided by ZPD1. Already ZPU1 divided by ZPD1 we derived without pass transistor. How much value it is? 4:1 or 4/1. If you substitute that one, the ZPU2 divided by ZPD2, we get it as 8/1. Okay, that is ZPU2 is 8 times of ZPD2. If you maintain this ratio, you can get the symmetrical operation, or without degradation the voltages we can get. Even the pass transistor is present in between an inverters. Okay, that is about the inverter ratio. Okay, so with the pass transistor the inverter ratio should be 8. Without pass transistor the inverter ratio should be 4. Okay, that is the derivation for the inverter ratio. In the next class you can see the switching characteristics of the inverters, so the time delay you can see.